Hello, everyone, and welcome to the new KAPA Target Enrichment webinar, Better by Design. The agenda today will start with our commitment to target enrichment, followed by a discussion of what is changing with our new offering and what is remaining the same. This will be followed by what you can expect, which are the improvements, features, and benefits. And we will also review the library preparation portion of our workflow. And finally, we'll wrap it up with discussing our custom probe design platform, HyperDesign. Roche has made numerous acquisitions, technology agreements, and internal R&D development projects to take substantial leaps towards a vision of a fully integrated end-to-end solution for sequencing. That's simple enough for potential clinical routine use. Before we start, it's worth spending some time to discuss where it all started about 20 years ago, where in 1999, Nimblegen was established in Madison, Wisconsin, which was based on a breakthrough technology that allowed massive and cost-effective long oligo synthesis on microarrays. In 2007, Roche acquired Nimblegen, and researchers working in collaboration with colleagues at Baylor University created a technique of target enrichment by using high-density microarrays to enrich specific sequences for next-gen sequencing on the Roche 454 Life Sciences Flex sequencer. Building on the first microarray-based exome, Baylor Human Genomics Center standardized on a Roche Nimblegen exome in 2010, sequencing more than 5,000 exomes in 2 years. Over the subsequent decade, Roche Nimblegen continued to invest in target enrichment and launched several innovative targeted sequencing solutions, which included exome designs, probes for targeted RNA-seq, methyl-seq, CCAP-EZ reagents, and Nimble Design, an online platform for target enrichment applications. In 2015, Roche made yet another NGS investment, acquiring KAPA Biosystems, which would include NGS library prep. This led to 2017 launch of HyperCap, which was a streamlined and fully integrated NGS sample preparation solution, combining library prep and target enrichment. And then jumping forward to 2018, Roche continued its commitment to target enrichment, and we updated our CCAP probe manufacturing to prime manufacturing, which was improved overall performance, delivering greater coverage of GC-rich regions. Launched CCAP Design Share, which was a collection of pre-designed NGS panels, and further advancing whole exome sequencing through our new CCAP Prime exome. And then lastly, we are making our latest investment in a new probe manufacturing technology, which is going to continue our commitment to target enrichment and further cement Roche as a leader in targeted NGS. In all these years, Roche clearly set the definition of capture efficiency while maximizing variant detection and minimizing sequencing at the same time. So where does that lead us? So what's changing is we've essentially upgraded our probe synthesis technology, which is giving us up to 30 times higher oligo fidelity, We also introduced several new and larger reaction pack sizes. Our order management, expert designers, and our third-party automation support team remains in place, and we're keeping our strong advances built through many years of experience in target enrichment. We'll continue to leverage our renowned probe design algorithm, expertise, and selection pipeline, the pipeline that was allowing you to access the most difficult genomic regions. We've also kept our online design interface Nimble Design. However, it's been enhanced to increase user convenience and streamline the design and ordering process. And now it's going to go by the name HyperDesign. And there's no need to worry about reestablishing your profile or saving your past designs. All of your user information and existing designs are transferred to HyperDesign, even your login and password. The protocol still relies on the combination of in-solution hybridization capture with biotinylated DNA oligos and high library conversion from the KAPA library prep kits. The new oligos are the key upgrade, but they are still deployed using the same renowned probe design and selection algorithm. The oligos are now longer with the fixed length 122 base pairs and have higher fidelity, which enables variable tiling used from a few hundred to more than 1 million probes. Focusing on the new oligos, which is the upgrade, we have the unique combination of 3 key features. Higher oligo fidelity, which is realized by using the KAPA Hi-Fi polymerase during manufacturing, targeting both DNA strands with double-stranded probes, both strands of which are biotinylated, pulling down more complexity from the libraries, and guaranteed presence and correct concentration by NGS-QC of all probes. So if we take a look at some of the advancements made to our HyperCap workflow with this new technology, several updated features are delivering additional benefits and improvement to the TE technology via updated HyperCap workflow v3. We're moving to a universal truncated adapter ligation, which is followed by sample barcoding using up to 384 unique dual indexes, which are used in the primers during pre-capture PCR amplification. We've also moved towards a one-sided size selection to retain more complexity going into hybridization. The HyperCap reagent and bead kits are similar to the existing with a few minor formulation changes. The improvements to the workflow itself include an increased temperature of the hybridization, capture, and washes at 55 degrees Celsius. And it is also automation friendly with the new 60 microliter hybridization reaction volume. And your speed back is no longer required. So what to expect? The KAPA target enrichment portfolio features both a new exome and custom designs. Before selecting the content of our exome, we interviewed many key opinion leaders in the field of routine whole exome sequencing. The vast majority of them favored an actionable and well-annotated coding context, as well as well-annotated, curated non-coding content, compact size for sequencing efficiency, and the ability to conveniently spike in additional content. The target is very similar to our CCAP Med exome. It targets content from CCDS, RefSeq, Ensemble, and ClinVar, and likely pathogenic variants of unknown significances and all of those databases. We also kept the unique features of sample tracking SNPs, which we first introduced in the prime exome, but we have increased the number of SNPs to 387. This is especially useful for high throughput workflows. This ensures sample integrity and quickly identifies potential mix-ups while avoiding the need to spike in additional controls in the samples. Before whole exome sequencing, the sample is briefly genotyped over those SNP positions using another method. After whole exome sequencing, in genotypes from sequencing are compared to the genotypes from the other method, confirming their sample identity. And for custom designs, you can choose to use our HyperDesign online design tool or interact with our expert designers. Either way, you'll benefit from 2 decades of probe design and selection expertise. So let's jump into a comparison study. Here we're comparing the KAPA TE hyperexome with a top performing on-market, fully rebalanced and optimized exome from supplier X. These exomes were sequenced proportionally to their target size. Both exomes captures were prepared according to the manufacturer's instructions and sequenced proportionally to their capture target size, and these exomes were 8-plexed pre-capture against a challenging sample set of 16 ethnically diverse Coriell DNAs to a total of 48 replicates per exome. HyperExome is the most uniform in this comparison with a fold 80 base penalty of only 1.45 versus 1.5 for supplier X. HyperExome's uniformity advantage is seen again when looking at percent of base pairs that are covered within a 2-fold around the median coverage. Our duplication rate is slightly higher, but the advantage of fold 80, median coverage, and the fold enrichment outweigh the additional 1%. and this can be seen in the following slide. As you can see, the KAPA hyperexome outperforms supplier X across these standard sequencing metrics. Even if the competitor has slightly lower PCR duplicates, this is not enough to translate in better target coverage and uniformity. The main take-home message from the exomes comparison are that hyperexome outperforms supplier X's exome by offering more meaningful content and better content coverage. The lower PCR duplication for supplier X doesn't seem to be enough to deliver stronger performance. Hyperexome is outperforming across all relevant sequencing metrics. And we also see an advantage in performance for a hyperexome as sequencing levels increase or become deeper. Here we see that more genes are completely covered at that 30x depth of coverage within those popular databases ACM G59, ClinVar, and CCDS, as well as 4,561 medically relevant genes that were identified by Roche through collaborations with key opinion leaders. For a reference, these were the medically relevant genes that were used in the development of our CKAP medexome. For our last set of exome performance metrics, we see that hyperexome is highly uniform and shows less GC% bias at either low or higher GC% regions than supplier X. The benefits of KAPA-TE technology are not only for our exome. Here we begin to see the advantages in custom designs of various sizes. Here we see results of custom designs prepared with the technology by using the previous CKAP easy designs as a basis. It's important to note that these designs have not been empirically rebalanced. Despite this, you can see the great uniformity and low duplication rate are achieved. Here we're showing a direct comparison between the CKAP design share neurodegenerative gene panel with its KAPA-TE version. The new version is slightly larger as we added some updated ClinVar content, and that's why it's proportionally sequenced more, 2 million reads versus 1.75. Both of these runs were on a MySeq 2x100 base pair run, and both of which were 8-plex captures. The CKAP version is a rebalanced design, while the KAPA-TE version is not. We just use the regions to prepare the design and test it. Improvement in PCR duplications is almost 4 times less PCR duplicates. Even before rebalancing, KAPA-TE version is performing with more uniformity. And this indicates that that new technology has a higher success rate right from the first version of your new design. And additionally, we'll be providing data proof of principle data sets for particular designs, including our hyperexome. This is a great way to explore the data for yourself prior to purchasing. If you're interested in running our files through your data pipeline, you can ask your genomic sales specialist or our support team for more info. So all the data previously seen was generated with our HyperCap version 3 workflow, which is our integrated protocol that uses KAPA target enrichment for selection with our KAPA HyperPrep and HyperPlus DNA library prep methods. This particular data was utilized using our enzymatic fragmentation of HyperPlus. So I'm going to talk about a little bit more about that workflow now. The KAPA HyperPlus DNA library prep kit is a workflow that utilizes a single tube to perform the necessary reactions for library preparation, providing an increase in library complexity and reduced sample loss. This increased conversion of sample to adapter ligated fragments also allows users to process lower sample inputs through a PCR-free workflow. Additionally, all of this can be achieved with fully automated methods on a number of liquid handling platforms with a processing time from 1.5 hours to 3. All of which can be completed with our single vendor source, because we can also provide KAPA adapters and unique dual index combinations, as well as our KAPA hyperpure beads. What I would like to address in the next slide is our flexibility to tune fragment size and compatibility with a wide range of DNA sample types. So on the left here, we're demonstrating the tunability of the enzymatic fragmentation with HyperPlus. We have a genomic DNA control sample at 100 nanograms that was incubated at 30 degrees Celsius with varying time periods ranging from 5 to 45 minutes. This demonstrates that a user can achieve the desired library size by simply adjusting the length of time of fragmentation. On the right, this chart shows that despite varying amounts of input and genomic GC content, there's little variability of fragment sizes between samples at either 5, 15, or 45 minutes of fragmentation. This can provide the user with robust and reproducible results across a range of sample inputs. So let's take a look at our core DNA library construction and how to predict sequencing quality that can be used for development and effective QC. We know from our work that absolute final yields are not good predictors of sequencing quality when you're comparing them across various sample types and inputs. We define this predictor within our core library construction process with how much of your input DNA is converted into adapter ligated library. Using this normalized metric, we're able to benchmark performance, and that's really guided our efforts towards making those performance and workflow improvements over the past few years. So as you can see, when assessing this core library construction performance, we continue to produce industry-leading library yields after adapter ligation. And this demonstrates a higher presence of properly adapter ligated fragments and an overall higher library complexity. So based on the results that we just saw, we're confident in our exome and custom designs. And through increased uniformity and lower duplication rates, we achieve higher target coverage at deeper sequencing depths, resulting in higher confidence for variant detection. This is combined with a streamlined, fully automatable HyperCap workflow v3, as well as our renowned design and content expertise. And we are committed to delivering superior service and support for our best user experience for target enrichment. So now we'll transition to how we can help you target your regions of interest with custom probe solutions and how to use our new tool, HyperDesign. When we launched the KAPA target enrichment product, we concurrently launched the HyperDesign website. This website is an improved custom oligo web interface that utilizes our renowned probe design algorithm and our team of live designers. It is intuitive and generates designs ready to review quickly. On your personal dashboard, you have access to resources such as KAPA target enrichment brochures, contacts for our online technical support team, as well as guides to help review and approve your probe designs. Also, you have a list of designs and statuses such as your drafts and designs that are ready for your review. When creating your custom designs, we have multiple ways that you can add regions. Manually inputting your desired genomic coordinates or specific genes of interest, attaching different files such as text files, bed files, or FASTA files, as well as add a link to an external source such as a URL or FTP server, all of which can be done in any sort of combination. And after you've submitted your design for review, you will receive a summary for your design you have submitted with a full report, and that contained estimated coverage. If you're content with the results of the review, you can simply approve your design, but if you'd like to have an expert review it, simply copy your design and check off the live designer button when resubmitting, and one of our experts will reach out within a few days. So for more information and support, you can contact your local Roche representative or email support.ckls@roche.com. Thank you for joining today's webinar about KAPA HyperCap and KAPA target enrichment, better by design.